So in this video, I want to take a little bit of time to talk about what's known as a common logarithm. We'll also talk about anti-logarithms eventually, and then do some work with the Desmos online scientific calculator to make sure you can use that site to do some evaluations with these ideas. So when you have a logarithm, there's almost always a little base that's shown down here as a subscript that's indicating the base of the logarithm. When that base is absent, you're dealing with what is called a common logarithm. And a common logarithm is a base 10 logarithm. Right? So our number system is a base 10 number system, and so the common logarithm is a base 10 log. So anytime you see just log, no base indicated, you assume that it's a base 10 that's being shown. So if I wanted to, I could put a 10 down here as the subscript on this logarithm. It obviously looks different, but it means the same thing. Calculators, whether it's a graphing calculator, a scientific calculator that you might use in a chemistry course, the online Desmos calculator that we're about to use here in a few minutes, calculators have the capability to evaluate common logarithms for you. They don't have the capability to evaluate every single type of logarithm. So this is going to be the type of logarithm, or one of the types, that you use most frequently. And so if we think about this particular expression right here, log of 100, or log base 10 of 100, that's equal to some value x. Well, if I change that to its equivalent exponential form, the base would be 10, the power on the 10 would be what I have as the answer to the logarithm, and then the result on this equation would be the value that's the input to the logarithm. So this one's pretty easy to figure out just by thinking about it in its exponential form. X is going to have to be 2. Now, there are going to be situations where you're not going to be quite, it's not going to be quite as nice to do what we did here. If your teacher, your professor is allowing for you to use a calculator and then round to a certain spot, or use the appropriate number of significant digits if it's a chemistry course or a science course, what you can do to evaluate expressions like these is you can break out your calculator. So directions here ask us to evaluate round to the nearest thousandth. Now, I'm not wrong to consider what I'm about to do here if I think, hey, this is equal to x. So what I'm going to do is I'm going to realize this is a common logarithm. So if I take 10 to the x power, what power do I raise 10 to? That was supposed to be an x there, sorry, to get an answer of 123. Well, there's not a nice power to put on this x that gives us an answer of 123. Can you ballpark it? Yeah, sure. You can think, well, 10 squared is 100, 10 cubed is 1,000, so I'm between 2 and 3 and way closer to 2 than to 3, since this value is way closer to 100 than it is to 1,000. So you can ballpark it that way, or you can get a little bit better degree of accuracy than just kind of a flat out estimate by going to a calculator. So the calculator that I'm going to show you here is the Desmos scientific calculator. So you can just go to desmos.com, you can just Google Desmos, and this will be the site that you land on. We don't want to do any graphing or anything. We want to use their scientific calculator. So if we choose their scientific calculator, once it loads up here, what you're going to notice is you're going to notice some stuff that's going to look familiar to you. You see sine, cosine, tangent. You don't see log anywhere on the main panel here. If you have a scientific calculator, a handheld graphing calculator, you will have a log button right on the main panel of buttons. On the Desmos online calculator, what we're going to have to do is we're going to have to hit this function key. So if we hit this function key, you get a lot more options that pop up, and one of them is a common logarithm. So if I just grab that option, I think the expression that we were trying to evaluate was the common log of 123. And so if we just toss in 123 into that logarithm, hit enter, we get that answer. So we can round that, what did it say, round to the nearest thousandth. So we can round this answer off to 2.0899. I guess it's going to get rounded to 2.090 if I was rounding to that degree of accuracy. If we wanted to go ahead and do one more of these, and I guess before we get too far ahead of ourselves, think about what we just said a minute ago. We said that we should expect an answer between 2 and 3, but way closer to 2 than to 3. So our ballpark estimate was correct, but obviously we have a higher degree of accuracy than we would have been able to get just by using the logic that we discussed a few seconds ago. If we think about the next evaluation we want to do, We can try to ballpark it if we want. This one's a little tougher. 10 to the 0 is actually 1. 10 to the negative first is 0.1, 1/10. So because this value is way closer to 1/10, way closer to 0.1 than it is to 1, we should expect an answer that's between -1 and 0, but closer to -1 than it is to 0. So you can always use that sort of logic to kind of figure out where one of these is going to sit when the numbers are manageable to do that with. But like we did last time, if the calculator's in play, fire that thing up. So we'll go ahead back here one more time. We'll toss in the log of, what was that, 0.132? Yeah, log of 0.132. Whoops, missed the 1. Try that again. And we've got our answer. And like we said a few seconds ago, we should expect an answer between -1 and 0, but way closer to -1 than to 0. And that's exactly what popped up. If we want to round this to the nearest thousandth, like the directions said, I guess we're looking at -0.879 is how that would round off. So the other thing that I want to address briefly within this video is what is known as an anti-logarithm. So if you're taking a math course, if you're in pre-calculus moving into calculus, you'll probably deal with exponential functions as the inverses to logarithms a little bit more so than you would within maybe a science course. So this would be notation that you'd probably be more likely to encounter in some of your work in chemistry. But an anti-logarithm is simply an inverse of a logarithm. Like I just mentioned in math, that's going to be an exponential equation. So if I have this expression here, the antilog of x is equal to a, that's only going to be true if I change it to the opposite expression, which is log, of the other side, that's going to be equal to x. So basically, if I apply the logarithm calculation to both sides of this, the log and the antilog cancel with each other, leaving us with just an x, since they're inverses of each other, and then I have log of a on the other side. So once you have it written as a logarithmic equation rather than an anti-log equation, it's a little easy, hopefully, to identify how it becomes an exponential situation. So the base is 10, right? There's no subscript on this log, so we know it's a common log, a base 10 log. So I take my base of 10. I know that on the other side of the log, that's going to be the power on the base, and then the input to the log is going to be the result to the corresponding exponential equation. So 10 to the x power is equal to a. We're trying to figure out what that value of a is. So here's one where it says find the antilog of 2.4. So my procedure here is to basically turn it into a logarithm situation as opposed to an antilog situation. So if I assume the antilog of 2.4 is equal to x, if I take the log of both sides of that, I'm going to have log of x, and then the antilog and the log are going to cancel, leaving me with just a 2.4 on the right. This is a common logarithm. So if I take my base of 10, I raise that base to the power that's over here, that's going to give me an answer that's equivalent to the input to the logarithm, which is denoted by the x. So 10 to the 2.4 power is going to be the antilog of 2.4 through the definition and the little sequence we just went through right here. And that's something that's easy to do on Desmos as well. So the calculation we had to do there was 10 to the 2.4. So if I just go 10 and then to the 2.4 power, we've got that result. So 251.189, I guess, if I'm rounding that to the same degree of accuracy. So hopefully this has allowed you to kind of see what common logarithms are, do some basic computations on the calculator with them, and we'll be doing this to basically wrap up our time this year.